Hello, Calculus 2 champions. What we'll be doing today is just we continue what we started last time. Remember, so far we covered section 6.2, 6.3, 6.4. 6.5 is not included in our syllabus, and today we'll be covering the last section in chapter 6, which is about the improper integrals. Now, what do we mean about the improper integrals? If we just start by looking at this example, okay? This is an example of an improper integral with a discontinuous integrand. What do we mean by that? If we look at this integration, okay? We have the integrand of 1 over x squared from -1 to 2. You do the normal integration, we do the substitution from -1 to 2, it gives us -3 over 2. It looks all fine, this is correct integration. It looks like, okay, substitution is correct, but this integration is incorrect. What's the reason behind this? Why it's incorrect? The first thing we need just to think about, this is 1 over x squared. If you think about the graph of 1 over x squared, okay, remember the meaning of integration is just basically we need to find the area under the curve. So if I think about 1 over x squared, it should be always positive, right? This is, let's say I'm graphing, just sketching quickly. If I need to sketch the 1 over x squared, it looks like this and like this. And this acts like the asymptote here, the y-axis. So this is already always positive. This is always positive. So how come the integration gives me a negative value? So there's definitely something wrong. But where's the mistake? If you look at this function 1 over x squared, we know it's discontinuous at 0. And we are finding the integration from -1 to 2. And 0 is already in between. Now, if we think about this integration, the integrand here, 1 over x squared, is discontinuous at 0, which is within this interval. Notice that we're taking this interval is from -1 to 2. We're finding the integration, but it has an issue at 0. It's discontinuous at 0. So there's something wrong here. Remember, when you start just studying the differentiation and the integration, there was one condition important before you do the integration, which is the fundamental theorem of calculus. So which assumes that the integrand should be continuous. And this is invalid, okay? It's not correct. So that means the whole integration here is supposed to be incorrect. Now, how can we deal with these cases? Okay, if there's any point of discontinuity, what can we do? In these cases, we call the integral to be improper integral, that it has a kind of discontinuity, somewhere where it's undefined, discontinuous. Now, the idea how to deal with this, we'll go back to the idea of limits. Remember, when you just have anything like discontinuous, we can think about the limits. What can we do with the idea of limits? What they do is this. Let's say that this is this example. Look, we can consider this integration for 1 over square root of 1 minus x. Now, if we think about the discontinuity, clearly that this is discontinuous where we needed this to be defined or continuous. I need 1 minus x to be greater than 0, which means 1 should be greater than x. Okay, so x here should be less than 1 without equality. But here the integration from 0 to 1. So I have an issue where at 1 itself, it's undefined at 1. Try to substitute 1. It will give you 1 over 0, which is undefined. So it's discontinuous at 1. Clearly from the graph, this is the graph of 1 over square root of 1 minus x. it's discontinuous at 1. It has a vertical asymptote at 1. Now, what we're going to do, we'll take, instead of the integration from 0 to 1, we'll take it from 0 to r, where r is any point between 0 to 1. While we're moving closer to 1, you see, just like the idea of limits, we're moving closer to 1 from the left. We're moving r closer to 1 from the left. So we can find an approximation for this area under the curve. So basically what we'll be doing, notice that we're moving from the left side. So basically we can adjust the integration here from 0 to 1 originally. We'll take it from 0 to r, and then we'll take the limit for r approaches to 1 from the left. Remember, this negative sign means that it's coming from the left side. Now, if I need to find this integration, I'll do the normal way of integration. This is like, it can be simple substitution. Clearly, the derivative here is -1. So the integration here is equal to -2, 1 minus x to the power of half, minus 2 square root of 1 minus x. If I do the replacement from 0 to r, remember, this is like dealing with limits, normal limits. So what you need to do directly is just direct substitution. Okay, I'll try to replace r. I substitute r, minus, you substitute 0, and then check what will happen. This part is constant. 1 minus 0 is 1 to the power of half. 1 times 2 is 2. So this term here, all of this term is equal to 2. Now looking at this term, try at limit for r approaches to 1. Okay, let's try to replace 1. 1 minus 1, it's 0. Under the square root, so it's still 0. Times -2, it's 0. So basically this whole term here, the limit is exist and equals to 0. 0 plus 2 equals to 2. So the limit here is exist and it's equals to 2. So we can take this technique into a general definition. What can we do in any case where we have improper integrals? Something like this. So let's say that we have the function here is continuous on the interval from a to b. Let's say that we have an issue at b. Okay, it's continuous from a to b, and as the absolute value of f of x approaches to infinity, we can take x approaches to b, but from the left again. Remember, if it's upper bound, you take the limit from the left. So it's approaches to b from the left. You can always think about the interval this way. So you have a, you have b. If you take the limit before b, so it's approaches to b from where? From the left. It's approaches to b from the left. So the integration from a to b, let's say we have the issue at b itself. Okay, this is the problem where it's discontinuous. So we'll replace b with r, and we'll take the limit as r approaches to b from the left. Remember here, we start with the integration normally. This is the order of solution. We do what? We take the integration for f of x, then we substitute the boundaries from a to r. Lastly, the last step, you take the limit. Okay, and remember, the first thing when you deal with limit, we do direct substitution to see what do we get. And we check if the limit is exist or does not exist. Okay, if the issue is with a this time, the issue is with a, it's discontinuous at a, we'll do exactly the same technique. We'll replace a with r, and we'll take the limit as r approaches to a, but this time from the right. Notice this right and left, it's just like while it's approaches to. So see that this is a. If we're approaches to a, so we're coming from where? From the right side. It's approaches to a from the right side. Okay, so this is the definition we're gonna follow in the next few examples. So the first thing we need always to do to check the continuity of the function. If we have any point of discontinuity within this interval from a to b. This definition, maybe this concept, we're gonna use it later on a lot in chapter 8. So if the limit exists, so this improper integral, we call it converges to L. So this improper integral, we say it converges to that value, which is L. But if the limit does not exist, we say that the improper integral diverges. Okay, so after we just saw the idea behind the improper integral, what does it mean, what to do, what's the definition in that case, we'll start with our first example. So for this example, we need just to determine whether this improper integral from -1 to 0 for 1 over x squared dx converges or diverges. Okay, let's see what can we do in this case. What I need you always to check, please, in any question, if you see that any question as definite integral, even if we don't say that it's improper integral, you have to check whether it's improper or not. So you look at the function you have. Here I have f of x as 1 over x squared. Now think about this function where it's discontinuous. I know that this function is discontinuous at x equals to 0. Now, after you find the point of discontinuity or the interval of discontinuity, you check the interval you have here. Is 0 within this interval or one of the boundaries? Yes, 0 is here. So I understand that 0 is an issue in this case, okay? So I have an issue at 0. Is there anywhere any other issues? No, only at 0. Okay, so now I need to use the definition for the improper integral. What can we do? I'll start with the integration from -1 to 0, 1 over x squared dx equals to, so the issue at 0. So I'll say it's the limit, the integration from -1, I'll replace 0 with r, and I'll take the limit as r approaches to 0, but from where? The left. Remember, always the upper one from the left. 1 over x squared dx. Okay, perfect. Now what's the order? What can we do? You keep the limit till the end, remember. I'll start with the integration. So this integration equals to, I'll keep the limit. This integration equals -1 over x. And I need to do the substitution from -1 to r, okay? So this is equals to, still I keep just the limit till the last step. I need to replace r. Remember, when you do the definite integral, you do the substitution, you have to do the f of b minus f of a, okay? The upper bound minus the lower one. Okay, good. So the sign in between is subtraction. The operation in between is subtraction. So this is equals to what? -1 over r minus, so -1 over -1, it's 1. So it's -1. Okay, perfect. Now, when you deal with limits, remember the first thing you do just always when you deal with limits is the direct substitution. So any limit, you need to check if it exists, does not exist. You need to try which technique to use. You need always to follow the direct substitution step. Okay, let's do the direct substitution. See, what do we get? If I do the direct substitution with r approaches to r approaches to 0 from the left, so this is -1 over 0 minus 1. But this is over 0 from the left. So this is like a negative value. So -1 over 0, but it's coming from the left. So it's negative over negative. So this is -1 over 0, but from the left. So this is equals to what? Infinity. Minus 1, it's still infinity. So that means this limit, what? Does not exist. If the limit does not exist at 0, we can say that hence the integration from -1 to 0, 1 over x squared dx is divergent. Is divergent. Okay, so this is our conclusion. This question is divergent. Okay, perfect. Let's move to another example and see if we have what's the issue with the next one. I have this question here. Now we have the integration from 0 to 1 for 1 over square root of x, okay, dx. Again, I need just to think about the function. Always, I want you just always to check the continuity of the integrand before you look at the intervals in general. Check the continuity and then see the interval. We're looking from where to where? It's from 0 to 1. So now I have f of x as 1 over square root of x. This is discontinuous for anything. Remember, this is square root, so anything under the square root should be greater than 0. Okay, so anything for x less than or equals to 0, it's discontinuous. Now, is x from less than 0, so you could write it as from negative infinity to 0, it's discontinuous. Now, within this interval of discontinuity, is our boundaries involved in this? Yes, I have an issue at 0. Anything above 0 is okay, but I have an issue at 0 itself. So this is discontinuous at 0. I need always to remember that this is where I have an issue. Okay, we'll do exactly as before. So we'll start with the integration 1 over square root of x dx. I'll redefine it as limit the integration. I'll change now 0 into r. From r to 1 as r approaches to 0, this time from where? Yes, from the right, for 1 over radical, or you could write it as a power form if you like. Just do whatever you feel like. So this is x to the power of negative half dx. Just I rewrite this one into the power form. Now we'll do what? Exactly as before. I'll start with the integration first. Remember to keep the limit till the end. So I'll take the limit, r approaches to 0 from the right. Check the integration. It will be equals to what? 2 square root of x. And I'll do the substitution from r to 1. I'll do the substitution from r to 1. Okay, good. Let's see. So this is equals to limit. Remember to use the bracket. So this is 2 radical 1. So this is 2 minus 2 radical r. Great. Now, dealing with limit, again, remember always the first thing you do when you just play around with limits or solve questions with limits, you need to do direct substitution just to check what's happening here if I do the direct substitution. So with the direct substitution, this is equal to 2 minus 2 square root of 0. And it's positive. Okay, it's coming from the right. It's like positive value. Okay. Square root of 0 is 0 times 2, 0. So this is basically all of this term is going to what? To 0. So this is equals to 2. This is equals to 2. So this time the limit exists. So we say that hence the integration from 0 to 1, 1 over radical x dx is convergent this time. Convergent to what? Or converges to 2. It's converges to 2. Okay? So we saw the first example, 6.2. We had it as the limit does not exist, so it was divergent. For this question, we notice that it's convergent, so it's the limit exists, so the integration is convergent to the same number. It's convergent to 2. Okay? Hopefully all is clear by now. Now let's see what do we have next. Now, in the previous two examples, we noticed that the issue was with one of the boundaries. It's either like the lower bound or the upper bound. As I said before, that's why I was letting you try to check the continuity always in general. Sometimes maybe you have an issue in between, okay? It's not only A, B, maybe it's somewhere in between. So if I have the interval, I have the integration within this interval from A to B. But the function has an issue in between, somewhere here, C. So it's discontinuous at C. In that case, I'll do what? I'll take the integration into, I'll split the integration into two, from A to C, and then I continue from C to B, where you consider C as the point of issue. So this is the one which should be replaced by R. This should be replaced by R. Now it's two integration. How can I deal with their limits? One by one, I'll do the first limit, the second limit. If both of them converges, okay, if these limits converges to L1 and L2, then their overall will be converges to their addition, L1 plus L2. If one of these two integration, okay, if one of them diverges, then the overall will be what? Diverges as well. So that means I need to check anywhere of any point of discontinuity within this interval A to B. If there's any point of discontinuity, I have to split the integration. It's always good just to see the number line, just to see the path. What do you need to do? I'll take it from A to C, then I'll continue from C to B. Okay? Now let's try one example where we need to use this. Let's check. So I have this question. Still, you see, just they are letting you practice the same function, but with different intervals, with different point of issues. Now, if you look at the 1 over x squared, which we discussed already before. So I know quickly that f of x equals 1 over x squared is discontinuous at x equals to 0. Look at the interval here given. We have the integration from -1 to 2. And clearly that 0 is somewhere in between. I have 0 is here. So I need to split the integration from -1 to 0. And then I continue from 0 to 2. So I have like two integral. Okay, let's see what can we do. I'll start with the original one. -1 to 2, 1 over x squared dx equals to the integration. I'll split with the point of issue. -1 to 0, 1 over x squared dx plus the integration from 0 to 2, 1 over x squared dx. I like always just even to highlight the point of issue so I know that this is the one which should be replaced by R. Okay, try always just to make clear which one you replace with R so you don't do any mistakes. Okay, now we'll go back. I'll use the idea of limits. So this is improper integral. So this is the limit as R approaches to 0. It's the upper bound, so it's from the left. The integration from -1 to R, 1 over x squared dx. Plus, I'll do the same for the second one. R approaches to 0, but here from the right, I replace this with R to 2, 1 over x squared dx. Okay? Now I need to deal with each one of them separately. I have to deal with each one of them separately. If you look at these questions, if you just go back to our example number 6.2, in example 6.2, we took it from -1 to 0, which is this one basically. This is example 6.2. We notice in example 6.2, this was diverges. So if this first one diverges, do I need to check the other one? No. Once you have one of them diverges, no need to continue with checking. From the first one, if it's divergent, you can get your conclusion that hence the overall, all of it, from -1 to 1 over x squared dx diverges. Okay? So if one of them is diverges, no need to continue. You just decide that this is diverges. Okay, so now what we introduced in the first three examples, the first one we had an issue with the upper bound. We dealt with it easily. The second one with the lower bound. This third example, we have an issue in between. It shouldn't be in the middle, by the way, anywhere in between. So I had to split the integration into two integration. I did the first one, and then you deal with them separately, one by one. So the first one, we already explained it in details in example 6.2, and it was divergent. So that's why the overall is divergent. Okay, let's see now what do we have next. Now, we'll move to different endpoints. It's not only like interval from A to B. Let's say that we have one of the boundaries as infinity or negative infinity. Integration, if one of the boundaries is infinity or negative infinity, we still consider it as improper integral. Okay, so this is another type of the improper integral, which we see a lot if one of the boundaries is infinity. Okay, so what we'll be doing exactly the same thing. So I'll take the limit as r approaches to infinity. So I need r to be approaches to infinity. I need the limit as r approaches to infinity. So we get something similar to the previous definition. Same thing. The integration from a to infinity, I replace it, but here there's no right or left. Okay, we're going to r to be a very large number, approaches to infinity, sorry. And here r approaches to negative infinity if it's down. And we'll deal with the limit as r approaches to infinity or negative infinity. Okay, now we'll just deal with more examples about this case. So again, we have the same conclusion. If it's convergent, if the limit exists, we say it's converges to L. If not, it's divergent. Now we look at this example. This is the integration from 1 to infinity. 1 over square root of x converges or diverges. We need to check. I need always to check the continuity. This is fundamental, please. Okay, if you have any question, always check the continuity. You never know. Maybe we have more than one issue. It's not at the boundary. Maybe it's in between. Maybe it's both lower and upper. So you need always to check. So f of x equals 1 over radical x is discontinuous. Where do we have an issue here? I have an issue if whatever under the square root is negative or 0. So it's discontinuous for negative infinity to 0. Including 0, what do you think? Can I include 0 if it's discontinuous? Discontinuous, yes, including 0. Because we know the domain for this, what's the domain for the square root? The domain is anything greater than 0. Okay, not including 0. We can't have 0. If I have 0, then it will be 1 over 0. It's undefined. So that's why it's discontinuous. Anything less than or equals to 0. Now look at the interval. It's from 1 to infinity. Is this issue already within this interval? No. But I have still an issue at where? Infinity. Always, if you see infinity, negative infinity, it's improper. Deal with it as improper integral. Okay, so I don't have any other issue. I have an issue only at infinity. Okay, how do I deal with this issue? Again, I'll start with the definition. So it's 1 to infinity, 1 over square. You need always to write this first step using the definition. So this is limit. The integration 1, the issue is only at infinity, r as r approaches to infinity, 1 over square root of x dx. Perfect. So this first step, it has always a point, so you need always to write it. So this is equals to, we'll do the same thing. I'll keep the limit till the end. I'll start by finding the integration for this, which is equals to square root of x, and I'll do the substitution from 1 to r, and this is equals limit r approaches to infinity. Remember, upper minus lower, so this is 2 square root of r minus radical 1 is 1 times 2, 2. Now, when I reach to the limits, remember, always the first thing you do is direct substitution and see what will happen. So it's 2 square root of infinity minus 2. So square root of infinity is still infinity, times 2, it's infinity. Infinity minus 2, this is again equals to infinity. So this is all equals to infinity. So this limit is what does not exist. If the limit does not exist, what should be our conclusion in that case? So we can say that hence the whole integration 1 to infinity 1 over radical x dx diverges. Okay. So we've checked and finally we got that this is diverges. Okay. See now what do we have next? This is example 6.5. Now let's see what do we have in the next conclusion we have about something like this. Notice the previous question, I need you just to check the previous one. The previous one was the last one we did, not this. I think, yeah, we did still only one. So this is 1 over square root of x from 1 to infinity. Now, if you check with the recommended questions, you notice that you can have a conclusion about this integrand, 1 over x to the power of p, always if the integration from 1 to infinity. So you can always get this conclusion about this in general, that this is what, if p is anything greater than 1, so this integral always converges. If p is less than or equals to 1, it's divergent. Why this is helpful? It can help me in checking my answers, one thing. If this is any form of 1 over, like the previous question, it was 1 over infinity, 1 over radical x, which is basically from 1 to infinity, 1 over x to the power of half. So it's of this form, but p at that case equals to half, which according to this supposed to be divergent, and we already proved that it was divergent. Okay, so no need just to prove it, just I need you to know that. P greater than 1 converges, less than or equals to 1 diverges. You'll see later on we'll need it when we compare, when we use the comparison test, we'll use this fact, okay? We can use this fact with the comparison test. Okay, let's now move to one additional example. See now this example, what do we have? I have the integration from negative infinity to 0. So definitely I have an issue at negative infinity. This is first thing. Now always, whatever the question is, I need you always to check the continuity. This is x. It's continuous everywhere. It has no issues. The exponential function has no issues. So do I have any issue at any other point from negative infinity to 0? No. So the only issue here is at negative infinity. What can I do in that case? I'll start with the definition. So this is the integration from negative infinity to 0, x e to the power of x dx. It's equals, according to the definition, I replace the negative infinity with r, and then I take the limit as r approaches to negative infinity for x e to the power of x dx. Okay, now the first step, just I check the continuity. I use the definition. Now I need to do the integration. This is x e to the power of x. So remember, this is like section 6.2. We need to use the integration by parts. This is integration by parts. Okay, let's do the integration by parts here. I need to use u as x, and I need dv to be the exponential function of dx, du basically dx, v here the integration is equal to exponential. We'll multiply these two minus the integration of these two. So what I have here is, always try just to calculate the indifferent integrals separately, just prepare it. So this is for x e to the power of x dx equals to, remember the rule for the substitution method. We do the integration for u dv, it's equals to the u times v minus the integration v du, okay? This is from the video of section 6.2. If you didn't watch the video, you need to revisit the technique. Please go back and visit section 6.2. Now this is u times v, so this is x e to the power of x minus the integration of e to the power of x dx. And this is equals to what? X e to the power of x. The integration here is only e to the power of x. For sure plus c, but no need because this is definite. So now this is the integration. Okay, what shall I do now? I prepared the integration already. I have it. I'll go back to the integration here. So this is equals to, I'll keep this here. So now I have the limit as r approaches to negative infinity. We know now the integration. It's x e to the power of x minus e to the power of x. And I need to do the replacement from where to where? From r to 0. I need to do the replacement from r to 0. Okay, let's see what do we have. So this is equals to limit 0. Try to replace 0. You'll get what? E to the power of 0 is 1. I need you always to keep the graph of the exponential function in front of you. Just this is really helpful. This is the x-axis, y, and this is the exponential function. And this point, the intercept here is 1. Okay. So now I need e to the power of 0 is 1 times 0, 0 minus 1. So this is negative 1. The first part is negative 1. Negative 1. Okay, I'll replace r now. Negative 1 minus, replace r. So r e to the power of r. Remember, this is negative, negative. So this is positive. So plus e to the power of r. Okay, because it's negative and you multiply by these two. Now this is the integration. I replace the boundaries. Now the only step left is to deal with the limit. Okay, let's deal with the limit. Now this first one is negative 1. Done, finish. This last one is e to the power of negative. Let's do the direct substitution here quickly, just only down. So if I do the direct substitution, just to check, it's negative 1 minus, here I'll do negative infinity, e to the power of negative infinity plus e to the power of negative infinity. Now if you look at the curve of the exponential function, so you notice that e to the power of negative infinity, you see as x getting smaller, smaller, very small, this is approaches to 0. Okay, this is approaches to 0. As x going to negative infinity, y approaches to 0. So that means this term here, this term is going to 0 alone. And this is negative 1. Okay, we have it. Now what about this one? Negative, negative infinity, it's infinity times e to the power of negative infinity is 0. Remember, now what we're trying is just only the direct substitution for limit. So the first, last, okay, easy. Now the middle one. The middle one, this form should remind you of something you covered in Calc 1. If you get the direct substitution as infinity times 0, this is what we call the indeterminate form. This is the indeterminate form, which looks like infinity times 0. For the indeterminate form, you learned in Calc 1 that you need to rewrite it using any form of this. It could be 0 over 0 or any plus or minus infinity. I need to create this form to be able to use, remember that famous rule? L'Hopital's rule. I need to use L'Hopital's rule, which says that if you need to find the limit for 0 over 0, infinity over infinity, you need to find the derivative of the numerator divided by the derivative of the denominator. And then you try again the direct substitution. Okay? So now I need to create this form, 0 over 0 or infinity over infinity from this one. Okay, remember, we did that direct substitution to check. Now I need to go back to this. I need to find this middle limit only. So first, last, okay, we're done with them. I need to try only with the middle one. So what I need to do here, just prepare for this middle part. I need to do the limit for r e to the power of r as r approaches to infinity. So direct substitution, we notice it's infinity times or minus infinity times 0. So I need to drop one of them just to create this form, 0 over 0 or infinity over infinity. So this is limit. If I drop the exponential down, so it should be what? E, but it's to the power of negative r. As r approaches, sorry, this is negative infinity, okay? Negative infinity. Now you try the direct substitution again. So direct substitution here, you notice it's negative infinity times 0. Here, if you do the direct substitution, it will be equals to what? Negative infinity over e to the power. Now it's negative. Notice it's negative infinity, but there's another negative, so it's e to the power of infinity. What's e to the power of infinity? You look at the curve. E to the power of infinity approaches to what? Infinity. So now this is infinity now. So can I use L'Hopital rule in this case? Yes. If I change it into infinity over infinity or 0 over 0, I'm able to use L'Hopital rule. Remember, with infinities, no need to worry about plus or minus. It's just like infinity or negative infinity. Now, how do I use L'Hopital rule? For L'Hopital rule, you need to find the derivative of the numerator and the denominator separately, not using the quotient rule. Okay, it's not the quotient rule. So this is the limit. I'll do the derivative of the numerator, which is 1, with respect to r. So this is 1. The derivative of the denominator, it's negative e to the power of negative r. Now I'll try again direct substitution. It will give what? 1 over negative e to the power of infinity, which is 1 over infinity. And this is equals to what? 0. So what did I use here? You need to mention that. So here I use L'Hopital rule by L'Hopital's rule. I've used L'Hopital rule. Now notice that this limit here, the one in the middle, equals to 0. So now the one in the middle equals to 0. This one is 0. This one is 0, and I have only negative 1. So basically overall this is equals to what? Negative 1. So I can say at the end that hence the integration from negative infinity to 0 x e to the power of x dx converges to negative 1. Okay, so this is really an important example on how to deal with it. Okay, so we started with the question. This is a famous case of the need of using L'Hopital rule. And when you solve it, you need to justify, you need to show these steps, okay? You can't directly say it's 0. You have to show that this is the indeterminate form, and then you change the form into 0 over 0 or infinity over infinity, and you use L'Hopital rule. Okay, so you have to go through all of these steps. Now see what do we have next. If the integration has both ends with infinity and negative infinity, so just like you have two issues, right? Just like you have two problems at the two ends. So remember, with improper integrals, we can't deal with two problems at once. Okay, just like in real life. If I have more than one issue, more than one problem, I need just to split them into I'll deal with them one by one. So the idea here, just to split this interval, you take any point in between. The interval is from negative infinity to infinity. So I take any point in between, like A. But still, infinity and minus infinity are the points of issues, which should be changed into r. So I need to split it from negative infinity to a, and then from a to infinity. What should be a? Anything you like. But usually they use something easy for calculation, like 0 or 1, okay? If it's continuous at these points. So now let's see what can we do. See the next question. I have this. It's a bit similar to the previous one, but this is x squared. And the integration from negative infinity to infinity. Okay. Again, as usual, we need always to think about the continuity here. So x has no issues. Exponential has no issues. So I don't have any issue here. My only issue is at negative infinity and infinity. And I have to split this integration using the definition. So I'll start with negative infinity to infinity x e to the power of negative x squared dx. Okay, now since this issue has at the two ends, okay, so I have issue here and I have an issue here. So I have to split this integration. So I'll write it from negative infinity. Now we'll think what to use. And I'll continue from this new value till infinity. Now what can we use here? In general, you can use anything you like, any number between negative infinity and infinity, which is any value. But again, in general, it's easier to take something simple, so I'll take 0. Sometimes they take 0, sometimes they take 1. It's like easy for calculation. Okay, we took 0. Now still I need to follow the definition. So this is equals to what? Now where are the point of issues? That's why I like always to keep track of the point of issues, so you know which one you replace with r. Okay, so this is equals to limit for the integration from r to 0 x e to the power of negative x squared dx as r approaches to negative infinity. And the other one, same thing. It's the limit as r approaches to infinity, 0 to r, 0 to r, x to the power of e negative x, this is x squared x squared dx. Now, we need to deal with them one by one. It's always recommended to deal with them like one by one. If I think about this first one, both of them, they have the same function, the same integrand. Now, how can I find this integration? Separately, I'll do it at the margin just to prepare the question. So look at this integration. The integration for x e to the power of negative x squared dx. Now, in general, remember what we practiced before. Can I use the integration rules directly here? No. The next method I need to think about is the substitution method. That's why I always recommend that you think about substitution before by parts. If I think about here integration by parts, it will not take me anywhere. I can't solve it by parts. Because if I use u as x and dv as e to the power of negative x squared, this one we don't know its integration. You don't know. You know the one for x only. If it's x squared, you don't know its integration. So basically, I can't use the integration by parts. And many times if we introduce something similar to this in the exam, I always see that the students, they tend to think about integration by parts. And they lose the way. It will be like hard for them to continue, or they do it wrong. So try always to think in this way. Rules, next you think about substitution. If it can be solved by substitution, no need to think about integration by parts. So if I think by substitution here, clearly you can use u as what? The power negative x squared. So du will be equals to what? Negative 2x dx. Okay, I always prefer that you solve this equation for dx. So in general, you know what to cancel if you need to cancel anything. Negative 2. Now I'll go back to this question. I need to use the substitution. So this is the integration, okay? X, I'll keep X, e to the power of negative x squared is u, so I'll call it u. Now what's dx? I did it here. It's du over negative 2x. Now see what can you cancel? X with x. So you have here negative half the integration of e to the power of u du. And this is equals negative half e to the power of u. And the last step should be the back substitution. And this is equals to negative half e to the power of negative x squared. Okay, so this is what we have as the integration. I've used the substitution method here, but I make it in details because I know it's a weakness. A success step always is this one. Trust me, if you add this step always, many students, they tend to do less mistakes. I see less common errors if they do this. So we start with our assumption, u equals negative x squared, du is negative 2x squared. I know that many students, they can see it directly. It's x dx, so you divide by negative 2. But I know many other students, they maybe multiply by negative 2. Or they do it in the wrong, and somehow they do it in a wrong way. So by this, if you think about what's dx, and then you replace, you have u, you have dx, cancel whatever can be cancelled. We took negative half outside. We do the integration. Last step is always back substitution. Okay, so now we know the integration. What I need to do, just I'll do one by one, okay? I prefer to deal with the issues one by one. So I'll deal with this first one, okay? This first one. So now its limits are approaches to negative infinity. Now the integration equals, it's already here. It's negative half e to the power of negative x squared. And we'll do the substitution from r to 0. And this is equals to, okay, we can take the negative half outside of the limit just to make it easier. If you kept it, it's okay. If you take it out, it's fine. So I replace from 0 to r. So e to the power of 0, negative 0, so it's e to the power of 0, 1, minus e to the power of negative r squared. Okay, good. Now what we'll be doing is the direct substitution. It's always recommended to start with the direct substitution. Let's try. So it's 1 minus e negative, don't forget the order of operation. It's again a common mistake here. This is r squared. I always recommend when you do substitution, use the brackets. It makes you really avoid any of these common mistakes. So I need to replace r with negative infinity. So it's negative infinity squared. Okay, so negative infinity squared, it's infinity. Times negative, it's negative infinity. So this is basically e to the power of, all of this is e to the power of negative infinity, which equals, as we saw before, this is equals to 0. So this is e to the power 1 minus e to the power of negative infinity. And this is 0. 1 minus 0 is equals to 1. And there's negative half outside, so this is negative, this integration. So it's down again. So this is equals negative half 1 minus e to the power of negative infinity squared. And this is e to the power of negative infinity. This is 0. And this is equals negative half. So this is the result of the first part, the first integration, negative half. Now I need to move to the second one. I need to do the other one. Same way, exactly the same thing. Let's try to do the second one. Let's call this one I. Okay, so this is I, and this one we'll call it, let's say, J. Now we'll move to J. So we need J, the other integration. Remember, what did we have? We used I, and it was negative half. Now I need to deal with J. So this is the limit as r approaches to infinity from 0 to r for x e to the power of negative x squared dx. Remember the integration, we already just found it in the previous slide, so it was negative half e to the power of negative x squared. Okay, so this is equals limit r approaches to infinity negative half e to the power of negative x squared, and we'll do the replacement from 0 to r. Okay, good. And this is equals, I'll take negative half outside, limit r approaches to infinity for e to the power of negative r squared minus 0. Notice here it's e to the power of 0 is 1, so this is negative 1. Now we'll do the direct substitution step. This is equals to negative half e to the power of negative, and this is r squared, which is infinity squared, minus 1. Okay, so this is e to the power of negative infinity, basically. So e to the power of negative infinity, this is equals to what? 0. And there's negative half times negative 1, so this is equals to half. Now overall, hence, the whole integration from negative infinity to infinity x e to the power of negative x squared dx equals to what? The first one, which we called I, it was negative half. And this j, the second one, is again half. So overall, if you add them, this is equals to 0. So we can say is converges to 0. So this overall integration is converges to 0. Okay, great. So now we see just there's really this section is just heavy one. And it has nice idea that you can deal with. You can solve from using L'Hopital rules, different types of integration. So this is the section that we can combine two sections together. So it could be, okay, it's improper integral, but the question you can use, let's say, the partial fraction method. You can use integration by parts, any of the method that we have learned, but we can make it as improper integral. So always it's recommended that you do the question into two stages. So you look at the integration as indefinite, solve it with any method you like, anything you just, you see it's suitable for that question. After you're done with the indefinite integral, you just check the different integral and then you continue with your solution. Now see what do we have next. In general, this is what we faced in the previous question. So again, in general, what I need you to think about that we can't have two problems in the same integration. Two improper, the improper integral can't have two issues, okay, at once. So anytime I have two issues, I can do this. This is wrong, okay? So I can't say the limit for r approaches to infinity from negative r to r. I have to split the integration. You have to split it, fine? If it's infinity, negative infinity, or any other number, same idea. Okay, now let's see this question. We need to check whether this integration from negative infinity to infinity for e to the power of negative x is divergent or convergent. Okay, same thing. I look at the function. I always have to check the function. It's e to the power of negative x, it has no issue. The exponential always is just like a lovely function, doesn't have a lot of problems because it's continuous everywhere. So it's continuous everywhere. So I have an issue at negative infinity and infinity again. So here are my 2 points of issues. Okay, so I'll do what? I'll follow the definition. So this is the integration from negative infinity to infinity e to the power of negative x dx equals, you split with what? I split with 0 again. You could use anything else. Plus from 0 to infinity e to the power of negative x dx. I'll follow the definition completely. My issues is at negative infinity and infinity. I need always just to see it to be sure what I'm replacing with r. So this is the limit of r approaches to negative infinity plus limit from 0 to r e to the power of negative x dx as r approaches to infinity. Okay, so far what I've done, just as only I've checked the continuity, if there's any issues. Definitely, if there's negative infinity, infinity, they are an issues. So both of them issues, so I had to split the question into two integration, okay? Now, once I split the question into two integration, I need to check one of them, one by one. Okay, I need to check one by one. So I'll take the first one. Okay, I'll take the first one and I'll see. This integration is easy, no need to prepare. We know that the integration for e to the power of negative x dx equals to what? Negative e to the power of negative x. So it's straightforward. Okay, I'll deal with the first one. I'll deal with the first one. So it's equals to the first one. Limit. The integration is negative e to the negative x from r to 0, and the limit as r approaches to negative infinity. And this is equals to negative, I'll keep the limit. Okay, so this is e to the power of 0 is 1, okay, times negative, so this is negative 1, minus, the rule has negative in between, and there's already negative, so this is plus e to the power of negative r. Okay, so it's negative 1 plus e to the power of negative r. I deal with now with limit. I'll take the direct substitution. It's equals to what? Negative 1 plus e to the power, it's negative r, and r is negative infinity, so it's negative infinity, which is infinity. Now e to the power of infinity is infinity. Minus 1, it still equals to infinity. So that means this limit is what? Does not exist. So my conclusion now, the first integration here is divergent. Again, do I need to check the other one? No need to check the other one. Okay, no need to check the other one. So from the first one, if it's divergent, I can make my conclusion overall. So hence, the whole integration for e to the power of negative x dx diverges. Why? Because this is diverges. So if one of them is divergent, you can get your overall as divergent. By the way, if you check the other one, this other one, you'll find it's convergent. And I need you just to do this part by yourself, just as practice. We were lucky that the first one is divergent, so no need to continue. But in general, let's say that the first one was convergent, then you need to check the other one, okay? If the first one was convergent, then I need to continue. I have to check the second one. But if the first one divergent, you can stop. No need to check the second one. But if you would like just to check it just for practicing, it will be convergent. Okay? Now our last example about these cases of the improper integral, we have this special case here. So I have the integration from 0 to infinity for 1 over x minus 1 squared. Again, as usual, I have to check the continuity for this function. If you look here, okay, numerator has no issues. Denominator can't be equals to 0. So if this can't be equals to 0, so basically x can't be equals to 1. So this function here, the f of x equals 1 over x minus 1 squared, is discontinuous at x equals to 1. So it has an issue at 1. So what does that mean? The interval here in general, it's taking from 0 to up to infinity, everything here. But 1 is here. 1 has an issue. And we need to continue up to infinity. Let's say I assume that this is okay, infinity. So I have to split the integration from 0 to 1 and then from 1 to infinity. Okay, now where are the issues? That's why I always would you like you to highlight the issues. Infinity is an issue, okay, and 1 is an issue. Is 0 an issue? No. So now I have 1 and infinity as 2 issues. So can I deal with this integration directly? No, I have to split again. So I have to split it with 1 extra number in between. What can I use? It's up to you. I'll use 2. Let's say I'll use 2 here. Why do I need to use 2? Just to avoid 2 issues at once. I need to avoid having 2 issues at once. So now what's the integration looks like? I'll take it from 0 to 1, then I'll continue from 1 to 2, and then from 2 to infinity. Okay, so it's like 3, not only 2. Okay, so this is an example of an integral that's improper for 2 reasons. I have 2 issues, at 1 and at infinity. That's why I told you from the beginning. Every time you see any question, you have to check the continuity before you look at the boundaries. But anytime you have infinity minus infinity, this is 100% improper, but still you have to check the continuity. So now this question equals to what? This is equals to, I'll take the integration. That's why it's good to have the number line. From 0 to 1, okay? 1 over x minus 1 squared dx. Then I continue from 1 to 2. And then finally from 2 to infinity. Now let's deal with them one by one. Where are the issues? So this is an issue which should be replaced with r. This is an issue. This is an issue. Okay. So this is equals to limit of the integration 0 to r 1 over x minus 1 squared dx, as x or r approaches to 1. Always, if it's constant, anything other than infinity minus infinity, you need to show it's from the left or the right. So this is the upper, so it's coming from the left. Okay, so this is the first one. I'll do the same for the other 2. Now we need to check this first one. We'll do them one by one, okay, as usual. I'll deal with the first one. So let's check only the first one. Okay, let's see this integration. This is equals to what? This integration here is just direct, it doesn't need much. So if I need to check the integration here, so this is equals to limit r approaches to 1 from the left for negative x, let's make it as fraction, negative 1 over x minus 1. Okay, and then I need to do the replacement here from 0 to r. Okay, this is equals the limit r approaches to 1, negative 1 over r minus 1 minus, let's check at 0. So 0 minus 1 is negative 1. Negative 1, negative 1 over negative 1, 1. So this is minus 1. Okay, do now the direct substitution. So it's always I need to check direct substitution first. So this is negative 1 over 1 minus 1 minus 1. This is 1 minus 1, which is 0. Okay, this is 0 basically. Down it's 0. Let's replace it. So this is 0, and up it's negative 1. Negative 1 over 0. Remember, how do you find the limit for these cases? Anytime you have a number over a 0, okay, so if I have like a over 0, where a does not equal to 0, what do you need to do? The limit here is always either infinity or minus infinity. How can you decide? You look at the signs. If both of them, they have the same signs, so it goes to infinity. If they have opposite signs or different signs, it goes to negative infinity. Now the numerator here clearly is negative. Done. I look at the denominator. This is 1 from the left. When we say 1 from the left, you can think about it. I like you to think about it as 0 point, okay, like 0.999, anything coming from the left. So if it's a small value like 0.999 minus 1, so it gives what? 1, but it's negative. That's why it's always from the left, it will give you something negative value. You try. 0.999 minus 1, so it's negative. Now it's negative over negative, so it's infinity. That's why the limit here usually it's infinity or minus infinity. So this one here is infinity. If you have infinity, very, very large number, and you take away only 1, so still infinity. It's still very large number. So the limit here does not exist, which is divergent. The first one is divergent. Now, if the first one is divergent, this first one here, do I need to continue the second and the third? No need. I'm lucky. First one is divergent, no need to continue. So hence the overall from 0 to infinity, 1 over x minus 1 squared dx is divergent. Okay, if one of them is divergent, then the overall is divergent. Again, I need just to emphasize on one thing. If you have, let's say, 3 integration, the first divergent one, you stop, it's divergent. But let's assume that the first 2 were convergent, then I have to check the third one, okay? So you don't stop unless you have one divergent. If the first one is convergent, then I need to continue with the second one. Let's say the second one is convergent, I need to check the third one, okay? So to be convergent, all of them should be convergent. To be divergent, one is enough. If one divergent, you can directly have the conclusion that it's divergent, okay? I hope this is clear. An important hence usually check the continuity. One advice, always, whatever the question is, you need to check the continuity. If there's infinity minus infinity, it's always improper. It's good just to see the interval on the number line, just to see how many integration do you need to split. And any point of issue, either use another color or highlight it. Just make it clear so you can follow. If you have 2 issues, it's impossible. I need always to deal. Remember, it's just like you can deal with 1 issue at once. I can't deal with 2 problems at once. 1 at a time. That's all. This is my maximum. Okay, so if there's 2 issues, you have to split again. This is the solution for the same question. Now, the only part left is an interesting idea, which we're going to use a lot in chapter 8. So now it's just like an introduction to this idea, the comparison test, but basically you'll practice a lot later on when we move to series, how to deal with the comparison test. Okay, so we'll have this more in details later on, but just in this section, it's just like introduction, the idea of the comparison test. So what's the idea of the comparison test, basically? The idea of the comparison test, let's say that you have 2 functions, okay, 2 curves, f of x and the curve of g of x. The one in pink is g of x, and blue is f of x. Now, when we think about as improper integral, it should be like from a to infinity, okay? We're thinking in this case about the comparison if it's from a to infinity. If the larger function, you look at the one in pink, if the larger one, okay, is convergent. So if the bigger one tends to, remember the meaning of convergent, that it's the limit goes somewhere, it has a value. So if the larger one convergent, so 100% the smaller one is convergent. So the big one is convergent, then the smaller one is convergent. Remember this, the large one is convergent. This is a useful case. If the larger one is convergent, then the smaller one is convergent, okay? Large convergent, it implies that the smaller one convergent, okay? Now, think in this way again. Let's say that this smaller one is divergent. I know that this smaller one, the limit goes nowhere, it's divergent. If I need to find the limit, it will be, does not exist. It will be like infinity. We can't just have this limit. So for sure, anything larger than this infinity or larger than this limit, which does not exist, will be also does not exist. So it takes me to the second case of the comparison test when I need to compare. So I know if the small one divergent, hence the larger one divergent. These are two cases. I always just ask my student to remember these two. LC is useful case, SD is useful case. If the large convergent, so I can easily say that the smaller one convergent. If the smaller one divergent, I can easily conclude that the larger one divergent. But what are the cases that takes you nowhere, okay? It doesn't give any conclusion. This is important, just to think about the non-useful cases. So if I know that the big one, okay, if I know that the big one is divergent, the big one goes nowhere, does it necessarily means that the smaller one divergent? No, it means nothing. This one gives no conclusion. It doesn't mean that the smaller one divergent or convergent. I don't know. It gives no conclusion, nothing. It means nothing. If the smaller one convergent, then the larger, okay, maybe I can add, let's say, the terms of the smaller one. I can find the limit for the smaller one. Does it mean that I can add the larger one? No, maybe the larger one is much bigger. I can't just find its limit. It's divergent. So if the smaller one convergent, also it gives no conclusion, nothing. Okay, that's why I told you I need always my student, I need them to write LCSD. Remember that this is the only two cases that can give me conclusions. This is the only two cases that they are useful. Because I see this as really a common mistake, especially later on when we move to chapter 8. So remember always, if the larger one divergent, it means nothing to me. It doesn't give any conclusion. Same thing if the smaller one convergent. Okay, so the only two useful cases are these two, LCSD. Okay, this is like a nice way to remember the important cases. Now, what does this is like an introduction for the coming theorem, which is this one. So this is basically what we've said. So if I have f is less than g and both of them are positive, so if the larger one, let's say, it's easier to recall, if the larger one, g of x convergent, then the smaller one converges. If the smaller one divergent, then the larger one divergent, okay? So basically what does this theorem say is just what I included already in the previous slide. So larger one convergent implies that, sorry, if the larger one convergent, the g convergent, so it implies that the smaller one convergent. But if the smaller one divergent, it means that the larger one divergent. So this is easy to remember. Okay, so this is the only two useful cases. This is really important theorem. We'll need this idea later on. Now, once we see the word comparing, comparison, that means we compare with something else. And remember, when you compare with anything, you should know the other one. So let's say I'm comparing the result of student A with the result of student B. If I'm able to say that student A got higher mark than student B, that's me and I know the result for student B. So you can't compare with something that you don't know. So that's why in general, when we use the comparison test, we usually compare with another function that we already know. Maybe it's one of the previous examples that we solved already, so we know the result already. Or it's one of the famous cases. Remember this one, I told you that we'll use it later on a lot. This form, 1 over x to the power of p. So with this one also I can know the situation according to the value of p. If it's greater than, remember, if p is greater than 1, it's convergent. If p less than or equals to 1, it's divergent. So this is something I can build the solution according to this, because I know it's convergent or divergent. I can easily decide. Now let's move to one example, the first example on using the comparison test for an improper integral. Now remember, if we need to use the comparison test, there's something fundamental we need to recall. that the comparison test gives me only a result that it's convergent or divergent. It doesn't really tell me its convergence to what. This is one thing you need to keep in mind. So it's unlike before, the questions we used to find its convergence to 1, convergence to 2, or whatever. For the comparison test, it's only let me know if it's divergent, that's it. If it's convergent, that's all. I don't know it's convergent to what. When do we use the comparison test? We use it if the question is something hard, we can't easily integrate. Okay? If it's something we don't know how to integrate. Okay, that brings us to the first example here, example 6.11. We need to determine the convergent or divergent for this integration. 1 over x plus e to the power of x from 0 to infinity. Now, if we look at this integration, do we know any rule for this integration? We don't. Notice that this is 1 plus x, and remember, don't do the common mistake. If I have 1 over a plus b, this can't be written as 1 over a plus 1 over b, okay? This is wrong. So this is not allowed. Now, what can I do? If we're unable to do this integration, I'll try to compare it with an easier function. What can I use as easier one? From this graph, clearly that if I think about 1 over e to the power of x, this shows the relation between them. So 1 over x plus e to the power of x is smaller than 1 over e to the power of x. It's not necessary that you know their graphs, okay? We could use the idea of inequalities to show which one is bigger, even if you don't need to graph them. The idea is this, just like you need basic skills in inequalities. So notice that in general, if I have x plus e to the power of x, okay? If I need to compare this with e to the power of x for a positive x, notice here x goes from where to where? From 0 to infinity. So for x greater than or equals to 0, which one will be larger? E to the power of x is the same. If I'm adding a positive value, even greater than or equals to 0, so this for sure greater than or equals to e to the power of x. Okay, so I'm starting with basic knowledge of inequalities. Now notice our function is the reciprocal for this one. Okay. If both of these two functions are positive, notice that e to the power of x is always positive. Exponential plus a positive value, it's again positive. So if both of them positive and I took their reciprocal, what will happen here in this case? So this is 1 over x plus e to the power of x. Remember this basic knowledge again. I need always, if we need to go back to any algebra, I rewrite it here. So if I have a less than or equals to b, and both of them positive or they have the same sign, if I take the reciprocal for them, I'll switch the inequality. Okay, notice like if you just take, for example, if you have 2 less than or equals to 3. So if you flip or you take the reciprocal for this, now half is greater than 1 over 3. Remember, this is valid only if both of them positive or both of them negative. They should have the same sign. Okay, using this fact, if I take this reciprocal, so this is less than or equals 1 over e to the power of x if both of them are positive, greater than or equals to 0. This is clearly, even without starting this step, if you look here, notice that this denominator is larger, so this fraction is smaller if you compare the denominators with each other. Okay, now what can we do? I'll try to figure out the integration for this part. So now we know that the integration from 0 to infinity, 1 over x plus e to the power of x dx is less than or equal the integration from 0 to infinity 1 over e to the power of x dx. Okay, now I'm interested in this part. This is easy, we can deal with this easily. Remember, when can this one be useful for us? The only case that's useful for us, since this is already larger, so I'm interested for this to be large convergent, the larger one convergent, to be useful. How do I know it's L? It's already larger. So the only useful case for me, if we are lucky, that it will be convergent. So we need to check. Let's see. Let's check. So I need to check this part. Now this integration here, the integration of 0 to infinity 1 over e to the power of x dx. Notice this is improper integral again. At where? At infinity. So I could write it as limit r approaches to infinity, the integration 0 to r for e to the power of negative x dx. And this integration equals to what? Limit negative e, the integration is the same but times negative 1, negative x from 0 to r as r approaches to infinity. Okay, very good. Let's erase this fact in here. Now, if I need to find this integration here, let's continue on the next slide from this step. So I reach to this step. So this is equals to the limit as r approaches to infinity. If I replace from 0 to r, so this is equals negative e to the power of negative r minus e to the power of 0, which is, I have negative with negative, so this is plus 1. Okay, notice the substitution, negative e to the power of negative r minus minus. Notice that the relation here, when you replace it, it's negative, and I have already another negative, so it's negative e to the power of 0, and e to the power of 0, you know, it's equals to 1. So this is negative e to the power of negative r plus 1. Now I need to take the limit as r approaches to infinity. Remember, always we try direct substitution first. Let's do the direct substitution. So it's negative e to the power of negative infinity plus 1. And what's e to the power of negative infinity? We did it before. Remember, I need just to check the exponential function. This is the exponential function. And this is 1. So e to the power of negative infinity, see, as x approaches negative infinity, it approaches to 0. So this is basically, this is 0. So this limit is exists, and it's equals to 1. Now what does that mean? If we go back to the previous slide, so now this here, the larger one, so hence the integration from 0 to infinity for 1 over e to the power of x dx is convergent. Now, what does that mean? Remember our comparison. So we have this large one, the one highlighted one, is convergent. So it seems that this is the case, that the large one convergent. So this implies what? That the smaller one convergent as well. What's the smaller one is our question. So hence, or so, whatever. So the integration 0 to infinity for 1 over x plus e to the power of x dx is convergent by the comparison test. By the comparison test. Now, notice again, can I say that this one convergent to 1? No. So the comparison test only gives me convergent or divergent, but it doesn't give me convergent to what? So they shouldn't be convergent to the same value. If this is 1, this one, I don't know. It's convergent, but we don't know to what. Okay, so the comparison test doesn't give me the value. It's convergent to what? Okay, so this is the first question using the comparison test. Now let's move to another one. Here, I have another question for the integration from 0 to infinity e to the power of negative x squared. Now, if I need to compare, let's first just look at the integration. Do we know how to integrate e to the power of negative x squared? No, we don't know so far. Is it like substitution? Nothing. I should have x outside if it's substitution. So there's no technique you know so far how to find this integration. Now I need to compare it with another function. Again, the usual easy one to deal with is e to the power of x or negative x. Now, if you know their graphs, it's fine, good for you. If not, I'm not just necessarily ask you to know the graph, but I just added the graph for you, so at least you can just imagine what's happening here, which one looks bigger, which one is smaller, what's the interval. But still, we can do that same as before, using the idea or using inequalities. Now, how can I start? If I start with x and x squared, okay, see, I'll start with x and x squared. Now, which one is bigger? X squared or x? This is if x is greater than or equals to 1. Take any number greater than or equals to 0. Which one will be, sorry, greater than or equals to 1, I meant. So if it's greater than 1, so for sure x squared is greater than x, right? But with fractions, it's different. Remember, if you have like half, if you square the half, this is 1 over 4. So x squared is not bigger. So it's true only for x greater than or equals to 1, clearly here. Now, I need negative. There's negative sign. What will happen if I take negative sign? It's just like you multiplied an inequality by negative. So what will happen in that case? You will flip the inequality sign, less than negative x. Remember the cases where you switch the inequality sign. If you multiply or divide by a negative number, you flip the inequality sign, or same case as before when you take the reciprocal. If both of them positive or negative, also you switch the inequality sign. This is the two cases where you'll be able to switch the inequality sign. Now that's okay. Again, this is for x greater than or equals to 1. Now I need to introduce the exponential function. I'll take the exponential function for both of them. Remember that the exponential function is increasing function, so it will not change the inequality. So I'll take the exponential for both sides. So this is e to the power of x still less than or equal e to the power of negative x. Same for x greater than or equals to 1. Now this is what we have. Okay, good. Can we easily deal with e to the power of negative x? Yes, so I can easily say that the integration from 0 to infinity e to the power of negative x squared dx is less than or equal the integration for 0 to infinity e to the power of negative x dx. Very good. Now I need to consider this larger one, just exactly like 6.11. Now I'm interested in this one to be what? To be convergent. I'm interested in this one to be convergent. Notice that this is exactly the same integration that we already calculated in 6.11 and it was convergent. So this large one is again convergent. So this one, the larger one, by example 6.11 convergent. Or even converges to 0, to 1. Converges to 1. Now what do I have? I have the large one convergent, which means the smaller one should be convergent. So I can easily say that, hence, the integration from 0 to infinity e to the power of negative x squared dx is convergent by, you need to mention you used what? The comparison test. Okay, so these are two questions where we tried just to build our question using the comparison test. Notice here I've used just some skills in inequality, basic skills. Just you need just to decide how to build your function. Okay. Okay. Now we'll move to one more, our last example on comparison test. Remember, as I told you before, the idea of comparison test, okay, now we're introducing it just slightly, but we're gonna just expand and we use it much more in chapter 8. So for now, it's just considered as like warming up, okay, for what's coming after. Now let's see the last question. This one we did it, this one. So this is example 6.13. I have 2 plus sine x over square root of x from 1 to infinity. Okay, now, again, we see the process. Do I know the integration for this one directly? We don't know how to find its integration. It's not an easy one. Okay, can I use substitution method? No. Integration by parts? No. So let's try to compare it with something we know. Now, when you have any question with sine and cosine, it's easy how to build your function, because we know that sine x, and this is also applicable for cosine, we know that sine x is always between -1 and 1. Now I'll try to create something similar to this. What do I need to do first? I'll add 2. So I'll add 2 for the whole inequality, plus 2 plus 2. So now you have 2 plus sine x less than or equals to 3, greater than or equals to 1. Perfect. Now I need to divide by square root of x. Remember here, for x greater than or equals to 1, this square root doesn't equal to 0. So I can multiply by 1 over radical x for all of them. So this is now 1 over radical x less than 2 plus sine x over radical x less than 3 over radical x. This is for x greater than or equals to 1. Now, if you just take the integration for these, I need to know which side will be useful for me first. Remember, this one, it's one of the famous ones that we can easily find. Remember the case where I told you that we can prove it from 1 to infinity for 1 over x to the power of p dx. And we said for this one, we know that this is, let's just rewrite it again here as r equals. So from 1 to infinity, 1 over x to the power of p dx. This is convergent always if p is what? Who remember? Yes, if p is greater than 1, and this is divergent if p less than or equals to 1. Okay, so our example here, we have 1 over radical x. So p is equal to what in this case? In our question, p is equal to half. So this is basically divergent. Now, which one will be useful for me? Do I depend on the left one or the right one? Remember, if it's divergent, so I need to use what? The smaller one to be divergent. The smaller one to be divergent. So that means this one is the useful one for me. No need to worry about the right hand one. Because this is the large one, divergent, it means nothing. No conclusion. So now I need the small one to be divergent. So I could write it in this way. So this is the integration from 1 to infinity, 1 over radical x dx less than or equal the integration 1 to infinity 2 plus sine x over radical x dx. Now this one, we can directly say that this is divergent. This is divergent. Why? Because p is equal. Later on we'll learn something. We'll use this idea as a p series. So because p is equal to half, so this is divergent. So this is the case of the smaller one, divergent. So hence we can easily say, hence the integration from 1 to infinity 2 plus sine x over square root of x dx. This integration diverges by the comparison test. Okay, so this is one case that it's divergent since the smaller one is divergent. So anytime we're using the comparison test, remember, if it's sine or cosine, we can easily build our function. Something like the one before, we can start with basic algebraic relations like x squared, exponential plus x. They are easy just to build. Now for this function, we know it's divergent because we proved this during exercises. But if you need to show it, you can easily show that this is divergent. You can easily show that this is divergent. And that's it for this section 6.6. And by this, we say goodbye to chapter 6. I'll try to add another video of problem solving, general problem solving on chapter 6, and then we'll move to chapter 9. Again, as usual, I remind you just to use Mika, okay, your AI assistant, just to help you while you're studying. Try to solve extra problems, try to write while you're solving, okay? Please don't read the solutions, it doesn't work like that.